Get my wet and dry rags here. But before I pull down this screen, I thought I would pause for a moment because I'm going to cover up what shows there the review. And so, as you know, we've been working towards the exam, and it's coming quickly. And so 1 week from today, next Monday, we will do exam number 3. And because of that, I wanted just to point out, before I cover this up, that Don scheduled a review for you on Saturday in this room here at 1 o'clock. And so I would encourage you to work that into your schedule the best you can. So the plan here for the week is the following. As you know, we got finished discussing chapter 11 when we on Wednesday, and then I trust that you've been working on the homework, if nothing else, hopefully a lot on chapter 10. We're only 1 week away. They do take a lot of time for this information to digest. And so what I've been saying for the last couple weeks, and we'll repeat it now, is you should spread out this over a long period of time. And hopefully you have been. And we are only 7 days away. And then we've got these last pieces of the material to cover before we get into the exam. So we covered the main material. We did two examples. I'll check here my notes. But let's go to a third example and a few more examples from chapter 11. And then once we finish those, let's go into chapter 12. And then we will have examples from chapter 12 on Wednesday. And then you will be ready for the exam on Monday. Okay, again, review on Saturday. And of course, as always, the workshop or the MC class on Friday. And so again, chapters 9, 10, 11, and 12 coming up on Monday. And then what time we have left after that, we will work on chapters 13 and 14. And so I'll call up the computer here, but I'm thinking we did 25 and 37, if I remember right. Let's look at number 37. But as we bring up the textbook here, let me jump to 37 here, make it full size. Yeah, this is the one where the bullet head hits the block. So these were the two that we got a chance to do. Both of them were a nice discussion on conservation of angular momentum, when it is conserved, when it is not. In fact, 50 does the same thing, and 56 for that matter. But let's go to 50 before we go to 56. And you'll see the same type of puzzle here. Here's 50. All right, so 50 says what? It says a projectile of mass little m, and so they've got a picture right below it here, moves to the right with a speed of vi. The projectile strikes and sticks to the end of a stationary rod of mass capital M and of length little d. It can pivot around a frictionless axis through its center. Okay? A. Find the angular speed of the system right after the collision. And then B, determine the fractional loss in mechanical energy due to this collision. Or put another way, find the heat that is created, or the fractional heat that is created. So same discussion that we had last Wednesday. Let's ask this. If I draw a picture of this rod, and I'll put a little dot here to indicate that it can rotate, and this little mass m moving with some initial speed is going to hit and stick to the end of this, and of course make this rotate in a clockwise direction. Now, that being said, I would like to ask the same set of questions. Is the energy conserved? Is the linear momentum conserved? Is the angular momentum conserved? And so these were our big three conservational principles that we've been building up to. And so I'll say it again, all of our mechanics is described by either A, Newton's laws of motion, those three laws, or B, the three conservational principles. Sometimes we need all three, sometimes we only need some of the three. But this is the first chapter that you have been exposed to the third one, and of course I think it makes the problems harder because then you can imagine they're going to be all three of them at the same time. And so running through this, remember we said energy is conserved, and I guess it's always conserved so long as we include, as we said, that little piece we had was other energies. Energies added to the system by some kind of outside influence. So in our case, I would say, yes, this is definitely true. I'll put a box around it. That's one equation that I will use. If I look at the interaction of those two together, I would say if I include all of the energies, that is the kinetic energies and the potential energies, and any other energies, particularly heat energy, or other forces acting on it, then I would have my conservation of energy. And so that was our first conservational principle. But the second one here was a little more discussion oriented about when is momentum conserved. And we had this discussion Wednesday. Let's say it again. When is momentum conserved? And I should say linear momentum. When? Yeah, the external forces add up to 0. Because if there are external forces, as we saw in chapter 9, then the momentum would change. It would change based upon those external forces. It actually gave us a recipe, as one of you pointed out in the last Wednesdays. What we could do is if there is an outside influence, like say the force of gravity, we could include the Earth into our system. And so then we'll have the two objects and the Earth. And then we would have conservation of momentum. That may help us or it may not help us. As we saw last Wednesday, that didn't help us much because when we included the outside influence, then we had another object that we knew very little about and its behavior, and so that didn't allow us to solve the problem. So sometimes it's kind of nice to include the outside world, so we do have conservation of momentum, and other times it is not, because that doesn't help us. And I would say this problem is exactly like that, because if you think about this thing moving along and hitting here, obviously there's an interaction, and maybe I'll in different color here say there is an interaction right here. The rod puts a force on the incoming mass. They don't really say what it is. Or maybe it's a wad of clay that sticks to the end like it did in our last problem. But obviously there's an interaction there, but that's not the only interaction. What's happening right here at this axis? And again, like we had on Wednesday, worth repeating here, imagine if that rod did not have an axis here. Again, let's just say it's as simple as a long piece of wood that you take and you drive a nail in it. With the nail in it, when this hits, it spins. But without the nail, what happens to it? Yeah, it translates. Now, it would probably spin also, but it would be doing both a rotation and a translational motion. And so without this piece here, we would have no external forces, and we would then have conservation of linear momentum. But that's not what we have. What we have is we have an outside influence. Let's say this is, nailed onto the wall, and so then I have an outside influence, and so what I'm trying to say, like we saw in the last one, is you would not use conservation of linear momentum for this problem. You would get into a lot of wrong answers if you did, because the basic principle is not valid of what we discussed in chapter 9, that we can't have any outside influences. And as one of you brought up on Wednesday, we could say, well, what if you want to include the wall, which is connected to the Earth? Okay, then you would have conservation of linear momentum. But then we don't have much information about the movement of the Earth, and so that's not going to be of much use to us. So I think our best approach is to say, let's just look at the two objects. Let's just realize that whatever happens here, the momentum before the collision is not going to equal the momentum after the collision. And the reason we know that is because there is this outside force. Which brings us to the main point of today's chapter, and that is these external torques. If the external torques are zero, then the angular momentum is conserved. Is it possible to have a situation where you have a force but no torque? And like we saw last time, yes, that is easily accomplished if either R is zero or the angle is zero. And so in this case, I would say, why don't we do this? Why don't we calculate all torques from this rotational axis? The advantage being that if you do, then the outside force, the one that made it so linear momentum is not conserved, gives us a torque still of zero, even though there is a force. And so we will have conservation of angular momentum, but only if we calculate it from that point. So don't pick some other point here or here or here or here, because if I pick, say, the point here to calculate all my torques, then this would give me a torque, and it would be from the outside, and therefore this would not be conserved. And so just like we saw a lot of these rotations, they're harder than translational motion because they involve the same principles, but they also involve distance. And distance involves where you do your calculations from. So things like torque and moment of inertia and angular momentum, how much value they have all depends on what point do you pick. And so you've got to think about what point you want to pick and why you would want to pick that. And I would say for this problem, I would want to pick this as the calculational point for the angular momentum. And they'll say it again, the reason why is because if I pick that point, then the torque is zero. And if the torque is zero, then the angular momentum is conserved. So even though this is not a conservation of linear momentum problem, it is a conservation of angular momentum problem, so long as I use that axis, and only if I use that axis. And that's what I want to make sure you saw in this problem just from the get-go, understanding. Then we can start to do more of your plug and chug type of things. Okay, what does the equation say? And then what I put in my variables, and then I solve. But getting up to this point is far more than just plugging and chugging. It's understanding the basic principles. When are they valid and when are they not valid? So I will, like I said, if I calculate angular momentum from the center of the rod, then I have conservation of angular momentum. And that's going to help, because if we come back to this question, the question says, find the angular speed of the system right after the collision. And so keeping this in mind, I know that before the collision, I have an object going in a straight line. And as I tried to point out, and you'll do the lab here today, part 3 of today's lab is very clearly trying to illustrate to you, does something that go in a straight line, does it have angular momentum? And yes, that's why we went through that long discussion on Wednesday, and you'll see it here in just a moment. Before the collision, I would have drawn out maybe that for my R vector. My angle then between them would be theta. And so if I call this then the initial angular momentum, then its magnitude would be R mv sine of the angle between the R and the V. And if you group this r together with this sine theta, and maybe you can see it if I draw the triangle out in green, there is the triangle, r being the hypotenuse of this green right triangle. So if I multiply it by the sine of the angle between them, we're looking at this distance, which is d over 2. And so before the collision, I have an mvd over 2 for the magnitude of the angular momentum. Now I know it's a vector, so it has direction. And maybe in passing here, I'll just put also the direction. I'm going to take my right hand and put my fingers in the direction of the first one, rotate my palm so I can close it towards the second one, which is the momentum, linear momentum vector. So r cross p, and I get my thumb pointing into the board. So the angular momentum is in the negative z direction. So I won't bother to put a negative k hat on here, but you can begin to see then that before the collision, this moving object, although it's a straight line, has an angular momentum, and it's in the negative z direction. And of course, once it hits and it begins to spin in a clockwise direction, I think then it is very clear that it has angular momentum in the negative direction when it is rotating in that clockwise direction. And so much easier to see, I think, the angular momentum once it is actually rotating. So that leads me to the other side of the equation. The other side of the equation says that the initial angular momentum has to equal to the final angular momentum. And so that would have to be equal to I omega. And so I will use the idea of angular momentum in terms of its inertia times its speed to then have these two sides set equal to each other. And I think that will help me answer the question, what is then the angular speed? mv d over 2 on one side and divide it by the I, the moment of inertia. Maybe I'll take one more step before I dive back into chapter 10. But one thing we learned very well, I think, in chapter 10 is that moment of inertia, again, is a very complex discussion here. You got to look at the shape of the objects you have here and how the mass is distributed. So I'm going to put the 2 there, but then I'm going to take I and say, let's look at the moment of inertia of this system. Once it makes impact, this big blob is sitting a distance d over 2 away. I will start with the long rod. What is the moment of inertia of a long rod? And I should emphasize about its center, because it is rotating about its center. Answer? Yeah, 1/12 m. And I'm going to use a capital M because that's what they said was the symbol for the mass of the rod, capital M. And it has a length of d, so I'll put a d squared. And so there would be the moment of inertia for the rod itself. Then the little blob that is sticking at the end would be m, and its distance away is half the length of the rod, and then I'll square that.
So how come for 1/12 md squared it's not 1/12 md over 2 squared?
Well, I guess that has to go back to the derivation. What we did is we took, this rod, and we said, here it is. And of course, we chopped it into pieces and said, let's add them together. But eventually, I know that it's pivoting here, so we had this integral that went from negative L over 2 to positive L over the 2. But the point is, the L meant the whole length of the rod. And so the factors of 1/2 is where the 1/12 comes from. And so remember, then the L meant the entire length of the rod. So it's a little subtlety difference between the final result we got for the rod, and then what do we mean by an individual chunk distance away? Yeah. Okay, well, keep moving along these lines. I've got the MVD still in the numerator, and I have a, well, I guess I'll leave the 2 right there. But I'm kind of thinking that maybe I will factor out a 1/12 because the 2 here squared, of course, is a 4. But if I multiply top and bottom by a 3, then 1/12 times a third is my 1/4. Right? And this 2 times the 12th makes a 6th. And a 1/6 can be flipped and multiplied and put in the top. So it's 6 MVD that goes into the numerator. And an MD squared plus 3 little md squared. Actually, it looks like a d can cancel off. Factor out at least one of those d's and break it off. And I think we finally get the 6mv in the numerator. And I'll even just factor out the d down here so that I get a capital M plus 3 little m. There we go. And so there's the answer that I think they are looking for. They didn't give me any numbers to work with, it's symbols. And so keep this in mind when they ask for something in symbols. What they mean is put it in the symbols that were given to you in the problem. So I didn't want to stop, say, here, although this is technically correct. It wouldn't be appropriate to stop there because it's in terms of moment of inertia. And a moment of inertia, you can figure that out in terms of the other parameters given in the problem, like the little m, the capital M, and the d. So we don't want to stop there. And so when we add that and then simplify it, I think we have come to what has been given. They've given little m and v and d for the length of the rod and the big M, right? And so those were the parameters given. So I think I've gotten to the what I'll call the symbolic answer to that problem. Of course, there's a part B. It's going to make us work a lot like we did the last problem on Wednesday. And that is, all right, how much of this kinetic energy is then lost? What fraction? It says determine the fractional loss in mechanical energy. That really brings up the second principle right here. The second principle is energy is conserved. And so as this little piece is flying in before the impact, I would say it has some initial energy, kinetic energy. Then it hits it and makes it spin. So obviously the fact that it's spinning means it has at least some kinetic energy. But as we've been seeing since chapter 9, that impact is a rubbing or a friction going on, and so there's going to be a lot of heat created here. And so this impact right here does have some heat that is formed. That is what they call the lost mechanical energy. That's what this question is asking. Determine the fraction of loss. So they don't even want to know really Q. What they want to know is the fraction that is lost. And so that's the quantity they're after. How much heat is created in comparison to how much did we start with. And so, of course, you might remember that I guess it was 2 weeks ago on Monday, after we came back from spring break, we did the conservation of linear momentum lab, and that was part of it. You were to shoot it. Was that before the break? Yeah, I think that's the one you did with Dr. Kelly. Yeah. Or at least 2/3 of you did. The 11 o'clock class. I was there before I had to leave. But we fired it in, and you had to calculate then the percentage of energy. And there was a lot of other questions in that one, which was why I always liked that lab. There's like you measure 3 things, but you are asked to calculate 9 different quantities. And so just a few simple measurements with the principle of conservation of linear momentum and conservation of energy, you can solve them. And this problem is nearly identical to that, except instead of having translational motion, we have rotational motion. So we have conservation of angular momentum, where we can get the angular speed after the collision, and then from that we can figure out in terms of energies. And this one is actually asking for the fractional loss. So solving for this, I guess I would get 1 minus the final kinetic over the initial kinetic. And so as I go through my algebra here, I would say, okay, what is the final kinetic energy? Well, since we now have a rotating object, I would say it's 1/2 I omega squared. And before the collision, we had a translating object only. And so the initial kinetic energy is 1/2 mv squared. And so clearing this off here, I'll keep working. But now this is the fractional loss. And you can see here that the 1/2s cancel off, so I'm not going to carry those through. That will keep it from being a compound fraction. That'll be nice. But I will get then my Q over the initial 1 minus, and I'll just write it first as, whoops, the I omega squared over the mv squared. But I think it's worthy to note then that this ratio of the angular speed to the linear speed is really what we had down here, right? This is the angular speed. And so if I take this v over here and move it to the other side of the equation, I then have the angular speed compared to the initial linear speed. And so putting that into here, this would be a 6m over a d over an m plus 3m. And it is squared, so I will square that, I will square that, and I will square that. And so that is the angular speed over the linear speed. And I still have a lot of mathematics to do in terms of simplifying this. I'll leave the bottom alone there for a moment. But we're back to this whole idea of what is I. And so if you remember, we got I right here by saying it is this 1/12, and then we factored it out here. So I'm going to put the 1/12 md squared plus 3 md squared in for the I. That's the moment of inertia that we did earlier, and probably worth repeating, right? The 1/12 md squared is the inertia of the rod, and then this is that little m and the distance from the rotation, which is half the distance of the rod squared. And then, of course, let's not forget this piece here, which is 36 once we square the 6, and then it is a little m squared. And so, again, looking at that, you can see that there's a lot of pieces that will simplify. Maybe I will start with the 1/12 going into the 36 3 times. Also, it's probably worth pointing out here that I can factor out a d squared and it would cancel with that d squared. There's 2 m's in the top and 1 in the bottom, so that can cancel off. And then, fortunately, to my luck and surprise here, that whole thing that's left is the same as that here, although there's 2 of them. So one of them will cancel with all of that. So it looks like in the top, I'm left with nothing more than a 3 times a little m. And down in the bottom, I'm left with a big M plus 3 little m. And so that's what I get after that much algebra. Now I still have more algebra to do. We can get a common denominator here, as we did, although very quickly at the end of Wednesday's lecture, and then realize that this would be the capital M plus 3 little m. That's how you would make this a common denominator. And then we would be subtracting the 3m from this piece here, leaving us with capital M over capital M plus 3m. And so there's our final answer on how much is lost to heat energy, what fraction. And notice again, it is a ratio that is connected to the masses. It's a little different than what we got in that lab 2 weeks ago. In the lab 2 weeks ago, we did not have this factor of 3 here. And of course, you can see where that if you trace that 3 back, you can see it comes from the whole calculation of moment of inertia. And so we didn't have that when we did the linear momentum collision. But nonetheless, we still did it in lab and in some examples in class when we did our linear momentum. So again, let me say it again. If you find yourself struggling with these rotational ones, the best approach to do is to step back and say, what would I have done had this been a translational problem? Okay, and I kind of erased the problem from up here, but I would say, what would I have done had I had a collision between 2 objects? And what I would have done is I would have looked at their linear momentum, and in this case, linear momentum is not conserved, but I would, like I said, I would look at those and say, this is how I would have approached it if it wasn't a rotational one, and use that as my guidelines so that I can do these rotational problems. Like I said, that's how the book is set up, and I think the best way to approach it. In fact, it gives me a chance to maybe give you a little bit of a hint. There is a tough problem that I'm hoping with those examples I just did, and the hint I'm about to give you, you won't find it quite so tough. But at the moment, I don't see it. Ah, there it is. And so it looks like it's number 36 here. But let's take a look at number 36. Again, this is on your homework, so I won't do too much here. But let's read it and talk about it, and hopefully you'll see that 36 is a lot like the one I just did, as well as the one we did on last Wednesday. But it says here that you have a puck. Now, this says a puck of mass 80 grams has a radius of 4 centimeters, so this is the smaller one, glides across an air table at a speed of 1.5 meters per second as shown in the figure. It makes a glancing collision with a second puck, so this bigger one, that has a radius of 6 centimeters and a mass of 120 initially at rest, such that their rims just touch. Because the rims are coated with this kind of this instant acting glue, so they kind of instantly stick together. Might have been a better problem if you just said there's Velcro on the rim. So they hit, they stuck, they stick together there. The pucks stick together and they spin after the collision. Here's the question. A, what is the angular momentum of the system relative to the center of mass? Now, notice they don't ask before or after the collision. Why not?
Conserved.
Is it conserved? Is the angular momentum the same before the collision as after the collision?
Isn't it 2 different systems? Or before they're together? Or separate?
No, but what we mean by system is the 2 objects. So before the collision, they're not stuck together. After the collision, they are stuck together. But our system being those 2 objects means that they interact with each other. Is there any other influence outside? No. And so that problem is a little different than the one we just did. The one we just did, we had the axis which supplied a force. Now we set it up so that the force provided us with 0 torque, which allowed us to say conservation of angular momentum. You might even argue in this sense, this one's easier. In the other sense, it's harder. But in this one, I would say it's easier because do you even have an outside force? No, there is no axis. So I would say the torque is 0 any place you want to calculate it. So is the angular momentum conserved? Yes. And it's not just conserved, it's conserved anywhere and everywhere you want to calculate it. So you could do it around the center of mass, it's conserved, but you could do it around any other point too. Now, I don't know if we really want to do it around any other point. I don't see the necessity in that, but we could. And this problem clearly says to calculate it relative to its center of mass. All right. Drawing this picture, where would the center of mass be?
Before or after the collision?
Well, that brings up a whole interesting question and discussion in itself. Yeah, before or after the collision. This is the part that I think is easier than the problem I just did. Although, as you're going to see, I think there are parts that are making this problem harder than the one we just did. But one thing that makes this problem easier than the one we just did, are there any outside forces? No. So what would you say about the linear momentum? It's conserved, right? And we didn't have that in the problem we just did. But here we have both principles, conservation of linear momentum as well as conservation of angular momentum. There are no outside influences. So when this thing, small one, is approaching big one, if you want to calculate the angular momentum before or after, they should be the same. If you want to calculate the linear momentum before or after, they should be the same. So I will draw a picture maybe before they collide. I'll draw another picture after they collide. After they collide, they are now doing what? They are rotating, and that's not it though. What else are they doing? They're translating, right? We have to conserve both the angular momentum and the linear momentum. The center of mass would probably be right about here. And so that center of mass would continue to move with some speed, and it would continue to rotate. And so these two stuck together would be moving across the table like this. They would be both translating and rotating. And because there's no outside influence, I know that whatever the momentum of the system is, it keeps it. So if it's the center of mass must go in a straight line. That's a key part to this. That is saying that this whole thing rotates around its center of mass. It's why the author actually said, go ahead and calculate the angular momentum about its center of mass. But had they not said that, I hope you would have been able to figure out that that would be the magical point you would want to consider. Because what we know is that this center of mass is going to be moving along, and it's going to keep moving at the same speed. So maybe before the collision, the center of mass, well, vertically would be about here, horizontally might be about there. And so as they come along, and when they make contact, the center of mass would actually be right there. And then after they make contact, the center of mass would continue to move at some speed, which we can figure out if that's part of the problem. I'm not sure. I'll keep reading here. But we know that the linear momentum is conserved. And that's easier than the angular momentum. But they did ask for the angular momentum, and we know that is conserved. And so I would say, well, let's figure it out from the, say, the center of mass. Of course, in this picture, that is a calculation based upon after the collision. But since the initial angular momentum is the same as the final, it is conserved, I would encourage you, and this is my hint for you, that I would calculate the angular momentum about its center of mass before the collision. So one of the things I would do first is find where is the location of the center of mass. So I'd go back to chapter 9 and think about center of mass. Once I found center of mass, then I would calculate what is the angular momentum before the collision, and then I know what it is after the collision. They don't even ask before or after because, again, it's conserved. You're supposed to realize that. But what is the angular momentum of the system relative to its center of mass? And again, I think it's easy to visualize after the collision. After the collision, you see it right here. You see it rotating around there. But in terms of calculation, I think it's easier to calculate before the collision. And so I would put my axis right there and say, what is the angular momentum? And clearly then, this one is moving in a straight line and this one is not. And then again, clearly, as we just did on this problem, does an object going in a straight line have angular momentum? It certainly can. Depends on what axis you pick. And so about the center of mass was an important clue there. And of course, B is, what is the angular speed about its center of mass? And of course, once you've done that, you can then realize that this is going to be I omega, whereas this side is going to be the R cross P, and we'll just do magnitude here. And so you can then divide by I, like I did in the last problem, in order to get the angular speed. Of course, there is some tough work here to do. Don't you have to get the rotational inertia, which is going to take us back to chapter 10. How do you get the rotational inertia? Well, you have to add the two objects together. They are both disks. So that's good. We worked with disks. Didn't we learn that the moment of inertia of a disk was 1/2 mr squared? Of course, that's about its center. Are these guys rotating around its center? No. So you're going to have to do the parallel axis theorem to figure out what the rotational inertia of each one is, because neither one is rotating around its center. And so that is going to be, I of the first one and I of the second one. And the first one then is going to have I of its center of mass and then some parallel axis theorem. And the second one is going to have its center of mass and its parallel axis theorem. And of course, they're different for each of the objects. And that's maybe too much of a hint. I made it easy on you now, so it's going to be an easy problem. But that's what I wanted you to see as we moved forward. Let's try another one. One more with conservation of angular momentum before we kind of shift gears on here. But I think a good, challenging one that really shows the fundamental physics of what's going on is number 56. Again, let's read it together to get the gist of the problem. But it says here, a solid cube of wood of sides 2a. Okay, and then they show a picture down here. Here's this cube that has length of 2a, 2a, and 2a. Okay. It has a mass of capital M, and it is resting on a horizontal surface. So in this picture, this is my horizontal surface, and so they're talking about this face of it, of the cube, down on the horizontal surface. They don't really show it well in this picture, but they say the cube is constrained to rotate around an axis, fixed axis, AB. So again, they don't really show what's going on here at AB. Maybe I can add more to the picture, but I do know they say it's fixed, meaning that the cube cannot slide. There's some kind of constraint. Probably the easiest thing for me to picture is just say there's like a set of hinges like you would find on a door. If I come over here to the door, I would see that this door is constrained to rotate on a fixed axis. It can't translate. It's got a set of hinges on it. And so maybe to add to that picture, I might say, okay, here is this cube, and going back into the board is AB, and maybe what we've done to this cube is to put a set of hinges right there. And to make it balanced, I'll put another hinge over here, and I'll just put 2 of them on there. This heavy door probably has 3. Yeah, there's a middle one there. But I'll just put those 2 hinges up there. Okay? And so that's what those words mean there. The cube is constrained to rotate around a fixed axis AB. So A and B is, it's set there. You can hit it all you want, just like that door. It's not going to move. It's going to rotate, perhaps, but it's not going to translate. It's fixed at AB. It then says a bullet of mass little m. So here they have the bullet, and speed v is shot into the face opposite of ABCD. So over here on the right-hand side is the face ABCD. The bullet is shot on the left-hand side. It enters the block at a height of 4/3 A. So they show this dimension here. The bullet becomes embedded into the cube. Find the minimum value V required to tip the cube so that it falls on the face A, B, C, D, and go ahead and assume that the mass of the bullet is much less than the mass of the block of wood. And I assume they are doing that, as you'll see here, because they don't really say where the bullet comes to stop in there. And so I think they want us to just say, don't worry about where it comes to stop. It just gets embedded. It does come to a stop. But wherever it is, it really hasn't changed the mass of the block. And it really hasn't changed the location of the center of mass of the block. And it really hasn't changed the moment of inertia of the block. And so we can ignore all the additional mass to that the bullet adds to the block. It's just so small. You'll see why that will come up as we run through all of this. But again, step 1, like all of these, is a good conceptual idea of what's going on in this problem. And so I think we've gotten there, that if I were then to fire this bullet at it, it would hit that block. The block cannot translate, but with this hinge here, what could happen is it would tilt up. And so if this is representing that cube as it was shot here, a slow speed may just barely make it kind of lift up, and then gravity would stop it and bring it back down. But a fast speed is going to lift it up enough that once it gets past this point, doesn't gravity then pull it the other way? And it falls down on the face, what they call A, B, C, D. And that's what they're saying. There's some minimum speed. If the bullet's going too slow, it will not tip it over onto the face. At some faster speed, and beyond that, it will tip it over to its face. And so we're back to the same questions we've asked on the last 2, as well as the hint I gave you on 36. Is this a conservation of, say, linear momentum problem? Are there any outside forces here? Yeah, there clearly are. And that hinge is providing a force in that direction during the impact, which is the whole reason that we have a fixed axis and it won't move. So, do we have conservation of linear momentum? No. Do we have conservation of angular momentum? Good. Yes, if what? If we measure it from that axis, which is perfect because that's where it's going to rotate anyway. So I've got no problems with that. In fact, that's probably where I would do it anyways without much thought here. But the external torque does equal to 0 even though the external forces do not equal 0. And of course, those external torques only come out to be 0 if you are calculating the torques based on this axis AB. So let's do that. Let's pick the axis AB as our reference point. And then we have conservation of angular momentum. But only then do we have conservation of angular momentum. And so then I can say the initial is equal to final. However, this is a little harder problem. Because what about gravity? As it starts to rotate up, what is gravity going to do to it? Right, gravity is an external torque, slowing it down. So it does change its angular momentum. So like we did with linear momentum, when we had friction, remember? Where we said, look, you could apply conservation of, and in chapter 9 we said linear momentum. Here I'm going to say conservation of angular momentum, but only if you do it during that impact. Because right after the impact, as it starts to move up, we have another external force called gravity that is taking angular momentum away from it and slowing it down. So I'm going to say that the angular momentum is conserved, but with the caveat that it is only conserved during that impact. And so you might remember from chapter 9, we did a problem just like this, where we had a block of wood and a bullet, and we fired it in, and then it slid 7.5 meters and came to a stop. And we asked it, was linear momentum conserved in that case? And obviously when it came to a stop, the answer was, well, no. But what we really meant was during the impact. If the impact was a short period of time and it really didn't have time for the external forces of frictions to act on it, we could say during the impact, angular, or excuse me, in that case, linear momentum is conserved. And then going across the sliding, then we have that external force of friction. Then we do not have conservation of linear momentum. Fair enough? And do you see this is the same problem? And so let me emphasize it again. If you come across a hard problem that has to do with rotation, you might be able to make it easier on yourself if you think about how would we have done this? Or in this case, how did we do this type of problem when we were dealing with just translational motion? And that's how we did it. We used the conservational principles during the impact and then said it was not valid after the impact. And same thing here. I am going to say that during the impact, the force we have is from the hinge. The impact happens very, very quickly. That being said, then there would be no real movement in a rotational direction. And so I would say that immediately after the impact, the angular momentum is the same as before. But then, as it starts to go up, then the angular momentum does change. And if the bullet over here is fired with a slow speed, then it would have an angular momentum that would eventually come to zero angular momentum, stop, and then gravity would pull it back down. And so we're looking for enough to tilt it over the top. And so as I think about all those options, I realize that I can apply conservation of angular momentum during the impact, but not after the impact. And so that's what I'll go ahead and do. And before the impact, I have an object going in a straight line. And so as we've done for many times, and we'll do in this problem, and on the lab coming up today, we will say that you could calculate the angular momentum initially before the impact by just looking at an object going in a straight line. And so, like we've done in the past problem here, I can draw out to the object coming in, R. Again, notice I am measuring from this axis. And if I make a right angle triangle out of all of this, where this is the angle theta between the linear momentum and the radius vector, I would have an r, an m, a v, and a sine theta. And if I put the r together with sine theta, I get the short leg of that right triangle. And that short leg is listed up there in the diagram as 4/3 A. And so there would be my first step. What is the angular momentum before the impact? And then, of course, that has to equal to the angular momentum after the impact. So I will just say final, and I'll just do magnitude, but that'll be an I omega. And so I'll just put here I omega. Now again, let me emphasize what this omega is, right? This is the angular speed immediately after the impact. Okay? And let me put a little circle around it to say, okay, there's applying the principle of conservation of angular momentum. But now let's think about what I'll call the second half of this motion. Now that the bullet has made impact and has given the block a certain angular speed, as it rotates up, doesn't it lose that angular speed? So it has to have enough and for it to go over the top, right? And so if this is A and this is B, give it a maybe I'll give it a little more twist in my picture. So here's A, and here's B. What is required for this thing to tip? Isn't that the idea for it to tip? You have to get what? Well, the center of mass, which started off maybe right about there. You have to get the center of mass to there, right? And again, this is another good example of you really got to understand the physics behind this before we can even decide what to do with our equations. Yeah.
I'm just wondering what A is in MB 4/3 A equals I.
What is this A?
Yeah.
Well, they said the block had a dimension of 2A,
Okay.
and the height is 4/3 A. Yeah.
But did you just consider magnitude equality because we had to calculate after? Or is it just the magnitude? Or is it the vectors after now?
Well, yeah, I'm only dealing with the magnitude of them. If we want to do direction, we would have the same direction on both sides. And so if I did it in terms of a vector, I would, say here is R, here is P, I'd get a negative K hat, which means when it makes impact, it has to rotate it in a clockwise direction. So technically there's a negative K hat here and a negative K hat there. Is that what you mean? To include the direction?
So is it just the magnitude or actually the two vectors are always equal?
Yeah, no, the two vectors are actually equal. Yeah, yeah. And so I guess I should have said the whole principle is, yes, the vectors are equal. So not only magnitude, but directions are equal. And then since the directions were obvious to me and don't give me any help to solve this problem, I just went to magnitude. So that's why I went to magnitude. Yeah. Okay. Well, anyways, this whole here is really going to allow me to do conservation of energy during the second part. And let me remind you, we did this in chapter 9. Remember that problem I was referring to? We had a block of wood, we had a bullet come in, hit it. We said linear momentum was conserved during the impact, and then it slid 7.5 meters before it came to a stop, and we did that part of the problem, what I'll call the second half of the problem, using conservation of energy. And that's what I'm going to do here. Look at the second half of the problem and how high does it have to swing up using conservation of energy. And so let me say energy initial is equal to energy final. Although let me be real careful about what I mean by initial energy. By initial energy, I do not mean the initial kinetic energy that the bullet has. The bullet has a lot of kinetic energy. It makes impact with the block. Probably most of that energy goes into heat, but some is clearly left over, which is making it rotate and moving on up. And that's the part of the kinetic energy I mean by initial here. That's what I mean. Is that after the impact, right here, there's a certain angular speed for it. That angular speed corresponds to a certain kinetic energy. So this block, as it is now moving up, so this initial is the initial it has after impact, but before it moves up. Okay?
So our system of consideration here is the bullet plus the cube.
Yeah, so my system is the bullet and the cube, yes. Since the bullet puts a force on the cube and the cube puts a force on the bullet, if I don't include those together, then I would have an outside influence and I wouldn't have conservation of angular momentum or linear momentum. So incorporating the two together, I can at least argue that I have conservation of angular momentum, at least during the impact. And of course, as this thing rotates, where does the energy go? If it has just enough energy to get to its highest point, then at that point I would say all of this kinetic energy has turned into gravitational potential energy. So notice that this energy, and if you want to do it as an inequality, this energy has to be greater than or equal to this value. It's got to get just to that point. I guess you might even say it has to be not even equal to, it just has to be greater than that. It's got to just barely get up there. And then gravity can take care of the rest and it'll fall over on the face A, B, C, D. But you got to get it at least to that point. Shy of that point, then it goes back down. Now, what about y equals to 0? Don't we have that freedom of choice of where to pick that during the problem? And I do want to be careful here because I claim I've already picked it. And if I'm not careful, I might forget that. Because over here on this side of the equation, didn't we say it was all kinetic, no potential? So if you're saying there's no potential, aren't you saying the height is 0 at this point? Okay, so where is y equals to 0?
Directly over here.
That is what I have either directly or indirectly, and probably indirectly if I didn't notice it or not, I am calling y equals to 0. So I'm not calling the ground y equals to 0, am I? I'm saying where it center of mass starts, which would be a distance of little a, okay, above the surface. So the center of mass is at a distance of, well, little a, okay? And that, if I'm going to use this equation, is what I am saying here for y equals to 0. So keeping that in mind, oh, and let me change my symbol here. What's going up a height y? It's big M, right? It's the block itself, ignoring the small m. So this little m was over here because this was the movement of the bullet. This should be then a capital M because it's lifting up the block itself. Now going to the next line, so here's big MG. What then is the value of y final? Right, and so good, I'm glad you see it. This right here in this position would be root 2a. So if I got to measure everything from this height here, this must be root 2a minus a. So that's how high we have to lift this block of wood. Okay? And then that would be 1/2 I omega squared. Now I can do a little bit of algebra here. I can say omega squared needs to be greater than, I'll put the 2mg over I in front. I'll even factor out an a and then get a root 2 minus 1 left over. And so that's what the conservation of energy is telling me here. Now, of course, this problem says that we need to figure out what the speed of the bullet is. Now, obviously, back in this first part, the speed of the bullet is connected to the angular momentum after the impact, and that's what this is. So, let me come back over to here. Let me write this then as a 4MVA over a 3I gives me my omega. So putting together the conservation of energy, which I call part 2 of the problem, together with part 1 of the problem, I have my omega squared. And so coming over here and clearing a little space, then I will have omega squared. So let me square all that. That'd be 16 little m squared, little v squared, little a squared over a 9 over an I squared. Has to be greater than, so there's the omega squared, a 2, a big M, a G, an A over an I times a root 2 minus 1. And we got a couple things that will begin to cancel off. I guess the 2 will go into the 16 8 times. Looks like there is an A on each side that will cancel off. And it looks like there's an I on each side that will cancel off. And so this 8 little m squared v squared over A over 9I has to be greater than big M G root 2 minus 1. And of course our goal is to find out V, so again let me move things around here. V squared then has to be greater than, and so I'll put the 9IMG root 2 minus 1 here. Divide that by the 8M squared A here. I guess I still need to take the square root, but I think yet another hard part of this problem, and so I suspect, is this a magenta? No, it's not even magenta, it's only blue. Okay, so it's not a hard one yet. Is to say, what is I? Because again, it's another symbolic problem. And again, you wouldn't want to finish the answer unless you put it in terms of the symbols they have given you. So let's go back to chapter 10 here and find I. And in fact, I'll just say, what is I then for that cube? Ooh. That doesn't sound so easy. However, if you do recall, way back in chapter 10, do I want to go that far? I probably should. We had that nice table. It's probably worth looking at. All right, here's chapter 10. So coming up somewhere close. It's still problems. Maybe I should just look up the page number and might be easier to find it. Oh, was that it? Bummer. Maybe I shouldn't have given up. Maybe it's the same way. All right, I'm going to find this table yet. Well, gotta be close, gotta be close. Guess I lied. Ah, there we go. Okay. And so here's this table, which it looks like it has a ring, a cylinder, solid cylinders, rectangular plate, rods, spheres. Uh-oh, no cube. What am I going to do?
Rectangular plate.
Huh?
We have the rectangular plate.
Yeah, we do have a rectangular plate. So why don't we start there? Because if I was working with a cube, I guess I would think of the cube as first made up of a sum of a bunch of plates. And so the cube is the sum of plates. So why don't I start there? I'll just add up a bunch of plates. Yeah?
Why can't we just say A and B are equal to make it a cube?
Well, that wouldn't make it a cube. That would make it a square plate.
What's the difference?
The third dimension.
Oh, okay.
But I am going to do both what you said and what I just said, because as you are pointing out here, if I just think of this as a plate that has a dimensions of 2a and 2a, and then I add a bunch of plates, I'll get my cube. So that's where I'm going to go with this. So I will have I of my cube, and I of my cube is going to be the sum of these plates, and the plates are actually a bunch of sum of rods. We don't have to go all the way back to rods and add up rods to get plates, but I think you'll clearly see they do have the 1/12 in there. It doesn't surprise you. And so I'll write that down as 1/12m, and they write it as a squared plus b squared. I just want to make sure it's clear what their symbols mean, because their symbols, what they give back in chapter 10, could be confusing for the symbols that I want here on this problem. For example, what is M? Capital M. This is the mass of the plate. It's not the capital M that is the mass of the cube. See, right? When I look up there, that capital M is the plate. It's not the cube. Now, don't get me wrong. A sum of a bunch of plates is going to get my cube. Yeah.
Can we call it D of M?
Can you call it what?
D of M? Is it like an elementary?
Yeah. And we might do that if we want to switch it to calculus. It turns out it's easier than that, so we don't have to go all the way back to calculus. But the point is that here this whole problem is, and this whole section is a good recipe of what I've been saying since the beginning here, is that these problems, you have to be reading and understand what each step means. You can't just say, oh, here's a formula, I'm going to plug it in. Plug and chug just doesn't work well here. Again, it's plug and chug. You'll get a lot of partial credit. You'll do okay. You'll get an okay grade. You'll transfer to an okay school. You'll have an okay career, make an okay salary, meet an okay spouse, and have an okay life, you know, with okay kids, right? So, there's a lot more going on to this details that I hope you will thrive for, going from just surviving to thriving beyond them. And that's the kind of thing that gives you that insight to be creative, to build that new product, to build that better product, and to do things that haven't been done before here. So that really means the mass of the plate. Let me continue on. What does the A and B in that equation mean? And how does that relate to this problem? Well, the A and the B are the size of the plate. For our particular problem, then, it would be 2A and 2A. So this should be 2A squared plus 2A squared. That is the AB squared. So again, the A that they show in that equation is not the same A that they have listed in this particular problem. You got to be careful and read and make sure I understand the pieces that are going on. Now let's see, can I erase that? Yeah, I guess I got my equation over here. Okay. And so what I have so far is that the cube is the summation of this plate. And let's see, if I square that, that's a 4. With another 4, that's 8. That would make an 8 over 12, which is 2/3, right? So let me write that as a 2/3. I've got the mass of the plate and the A squared. Okay? All right. So, not quite done. 2 more big steps for sure. One of them is to get the whole cube, I would have to add up a bunch of plates. And as you pointed out, that makes me think I should do some calculus. However, they were nice about it, because when you add up plate after plate after plate, doesn't every plate have the same dimensions? And so isn't this just the sum of the plates? And what would you say about the sum of the mass of all the plates? It's the mass of the cube. Again, notice I'm not really doing the math as much as I am reading the math here. And so I would say this is 2/3 A squared times mass of cube now.
Are you saying we get the same result if we integrate?
Yeah. Because at this step then I would just change it to an integral of dm, which would just give me m. Yeah. So there's the cube. Oh, so that's good. That's how I eventually went from the m being the mass of the plate to m being the mass of the cube. And it kind of makes sense that it really shouldn't change the equation no matter how thick it is. The thicker you make it, it's still rotating with the same dimensions. It just, the thicker you make it, the more mass it is. So we really have the same dimensions here for the mass of a plate, then we just change it really to the mass of the cube. So it doesn't surprise me it kind of came out that way. However, I'm not done yet. Because didn't we say the inertia has to be calculated about some point? And so what have we just calculated it about? It's center of mass, right? Didn't we just calculate the moment of inertia of the plate about its center? I mean, isn't that what's shown here in this diagram? So we don't have what we want yet. What we have is what would be the moment of inertia of a cube rotating about its center. But we are off center. But that's perfect. How do we get off center? The parallel axis theorem. So what I really have so far is the moment of inertia of a cube about its center of mass. So to get the cube about its corner, I need to move from the axis, which we've just calculated its center of mass, and move it over to its corner. And so the parallel axis theorem says if you know it around its center, you can then add to it this extra term, and that will get it off center. So I have it on center, which is 2/3. And let me go ahead and put mass times a squared. And if it'll be okay, not only will I put the m first, since that's kind of the tradition, but I'll even just drop the word cube for a moment, now that we've figured out that it's the plates were added together and that is the mass of the cube. And now to go off center, I will take mass, again, of the cube, and then the distance I am moving. Well, how far am I moving? Yeah, and so this distance is a, that's a, so I'm moving root 2a. So this would be root 2a, and I'll square it. Which, of course, when you square that, that is 2a squared. So I have a 2/3 plus a 2ma squared. That's this extra factor, which I guess is a common denominator of 3. So it's 2 plus 6ma squared. So that's 8/3 ma squared to get the moment of inertia of the cube. So now I can come over here and finish the problem finally.
To use the parallel axis, does the point have to be still on the object, or can it be?
No, it doesn't have to be on the object. It does have to be, and I didn't really emphasize this, again, being our first course on mechanics. But we could have moved it anywhere. Even out here, if this was like had a rod attached to it, a handle, you could still rotate it around some point. But the parallel axis theorem, as the name implies, must be another axis that is parallel to the other one. So if I know it around this point, let's see. So if I have a plate and I know it around this point, I can get it any other axis that is parallel to that one, but I can't get it around this axis, which is perpendicular to that one. That would require what's called the perpendicular axis theorem. And yes, there is one, but you're not introduced to it. So next time you take mechanics, we will get, or I say we, but it'll be you, because you'll be taking it at, say, UCSB or wherever you transfer to. You'll be doing the same one. And I'm sure your teacher will say, oh, you guys already know the parallel axis theorem. Let's go to the perpendicular axis theorem, because now we can do any axis we want, right? We can go from other axes that are parallel to ones that are perpendicular to that. Yeah.
Couldn't you just use the equation for the rod and just change L squared to A squared plus B squared?
No, I would not call a cube. I mean, I guess I'm trying to pick your brain here. What are you visualizing for the cube?
Well, like you said, the plate is just a summation of rods.
Yeah.
So the cube is a summation of rods plus a summation of rods.
Oh, okay. Okay, fair enough. Maybe I shouldn't have been so quickly to say. It would have been a hard problem, but yes, we could have added up rods. Because what we could have done is we could have said, let's add up that rod together with this rod, together with this rod, together with this rod. Of course, that would have just given us the plate. And then we would have added those up to get it. So yes, we could have started with the rods. However, when you are getting the plate, don't forget then that when you add that rod to that rod to that rod to that rod, each of these rods, you are at a different distance from its center. So it's not just as simple as 1/12 ml squared added up. It's the parallel axis theorem added up.
So how come it works out for 1/3 ml squared? Because I'm talking about the rod about its end. If you end up putting in 2a plus 2a instead of L squared, and then you square each of those values, you still end up getting 8/3 ml squared.
Say that again. I think we just got lucky. What did you say? Take 1/3?
If your L squared, you expand it into the a squared plus b squared, you'd still get 2a plus 2a, or 4a plus, or 4a squared.
Okay, so what are you saying I replace L with?
A squared plus b squared. So then that would be a plate about its end.
Yeah, but I'm looking for the justification. Why would you... I mean, you took a rod. I mean, this is really a rod that has a length of a squared plus b squared. It's not a plate. Yeah, so I agree it does work, but it's... Yeah, but not completely, because I think it is connected to the right angle Pythagorean theorem. The coincidence part is this Pythagorean's theorem is connected to the squares, and inertia is connected to the squares. But, yeah, not really completely justified, tell you. Add the Pythagorean theorem, what is proportional to the squares, and the inertia, which is proportional to the squares. But yeah, it does work. So I guess I'd say yes, it's coincidental for that particular geometry. I wouldn't want to do that to take a bunch of rods, say, to get a sphere, since they're each of a different length. Well, anyways, I better keep moving because there's so much I want you to see here. And you can see this is a long problem, a lot of details. But again, if the details make sense, then you're ready for the test. If they don't make sense, well, you got 7 days, right? And that's why we're doing the lab here today. And class on Wednesday, and workshop on Friday, and review on Saturday. That being said, I finally have now the moment of inertia of a cube from its corner, which is what I really want, and I can finally put that over to here. So v squared must be greater than, and I'll put the 9 and the 8 and the m squared and the a, and now I have my 8/3 big M a squared for the I, and then I have the m and the g, and then I have the root 2 over 1. And it looks like then things begin to simplify a little bit. 8 goes with 8. 9 goes into 3 times. So the prefactor is just a 3. It looks like an a downstairs cancels off, but it looks like I have an m and an a, another m squared, and a g, a root 2 minus 1, all over m squared. And since we did a lot, it's probably worth pausing and just saying, does this even make sense? How about the units? Mass would cancel with mass. That'd be a length. Yeah, that'd be meters squared per second squared. And then they would match. So at least the unit analysis works. And then one final step is I will take the square root then and get rid of that. So there it is. The speed has to be greater than that value. Yeah.
How does the square root affect the units?
Well, units always do the same thing with your units that you would do with your numbers. So if I was doing a calculation and I said v squared is greater than 64 meters squared seconds squared. When I take the square root, I have to take the square root of the first factor, the square root of the next factor, the square root of the denominator, right? And so the square root of 64 is 8, plus or minus, plus 8. Then there is the square root of meter squared, which is a meter, and the square root of second squared, which is just a second. And so, again, I said it in chapter 1, but it's worth repeating. When you ever come across something you're not sure with your units, the same mathematics, whether it be calculus or trigonometry or logarithms, or in this case, square roots, you do the same properties of mathematics for the numbers that you do with your units, and that you also do with your unit vectors, too.
What about exponentials and logarithms? Don't they like change?
No, they get a... they do get... the units do get hard with logarithms. But they do follow the same rules. For example, if I were having like 10 meters for whatever reason, and I want to take the log of 10 meters, I would write that as the log of 10 plus the log of a meter. So the first term has no units, and the second one I really can't simplify anything other than it's the log of 10. But the point being, if the log of 10 is 1, okay. But the point is, I would have some weird looking units. Instead of having a number and then multiplied by the unit, I have a number and then added to the log of the unit, which usually doesn't serve us any purpose unless we're trying to undo it, for example. Let's say we then go to raise that to a power back of 10. Then we would say this is a power of 10 times a power of the log of meters. And then so that's a 10, and the logs undo themselves, and we're back to the units being multiplied together. So they work. They will always work. But I got to admit, logarithms is probably the most confusing one, more so than any of the units involving calculus. Yeah. So a lot of times what we do is, because it's added to it, we just kind of drop it, and we always just do numbers, and we say, oh, they don't have any units. But it's not quite true. And then we throw it back in at the end. Well, and that's not quite true. We kind of cheated ourselves of the true principle of dealing with units when we do that. So yeah, that's a good one. All right, well, let me jump to 58, 59. They kind of dovetail together, and these are the last two I was planning on doing. I don't think they're necessarily any harder than the ones we just did, but I guess your author does, because he puts it down as magenta. And so let's look at some magenta ones now that we've done the easy ones, which I'm sure they didn't look that easy. They were kind of long here. But as I said, this material is really the meat of the semester here, and dealing with rotations. As I said, partly because rotations, I think, are just more complex in general, because instead of having inertia, you have rotational inertia, which doesn't just depend on mass, it depends on the distribution of the mass. And the torque it's not just a force, it's got a lever arm, and it's got an angle as well as a force. So all the things with rotation are just harder. Also, I think they are less, you've had less exposure to them. You've probably been doing simple translational stuff, maybe even in a science class in 5th grade. You had things like, hey, let's introduce you to Newton and action-reaction forces. But you didn't really do with rotations. And so the idea is to get students to really get a good understanding of translational motion, and then use that to introduce them into rotational motion. And so probably the first time you really started doing rotation was probably in your Physics 102, maybe a little bit in your high school one. But none of that did it to the level that you are obviously seeing here at this level, where we have calculus thrown into the mix, which obviously you can see you can't really do any rotational mechanics without the calculus, because you got to add up the mass distribution to get the moment of inertia here. And so it really takes where you are now in your education. And so you're seeing some new stuff and some hard new stuff. If it makes you feel any better, you're doing as much as Newton did. You're as smart as Newton. Okay, well, at least you're doing the same physics Newton did. He was a very smart guy, obviously, here, and but he had to develop calculus. He didn't have calculus, and some of you are already on Calc 2 and going into Calc 3. You know more calculus than Newton, and so you've gone on to multivariable calculus. And next semester, when we get to electricity and magnetism, then we can say we know more than Newton ever did. And so it's not easy stuff. That's, I guess, why I keep saying you got to spend some time on this. All right, well, let me go to number 58, and I'm going to, instead of flip all the way through there, look up what page this is on. And so number 58 is on 336. So I'm going to jump over here and go 336. There we go. And say, all right, what is number 58? And it leads into number 59 here. It says a uniform solid disk is set into rotation with an angular speed omega I about an axis through its center. While still rotating at this speed, the disk is then placed in contact with a horizontal surface and released as shown. And so here is the as shown. So it's spinning and you set it on a horizontal surface. A says, what is the angular speed of the disk once pure rolling takes place? B, find the frictional loss of kinetic energy from the moment the disk is released until pure rolling occurs. Now, this is, as I said, probably worth showing, because I don't know if that picture gives a full and fair description. Here it is. Spin it. It's rotating on initial speed. Set it on a horizontal surface. What happens? All right, so as it is spinning here, when you make contact, isn't there some kinetic friction? Isn't there some sliding going on? And that sliding then is going to create some friction, which that friction is what pushes that forward. In fact, let me start right there. What direction is the friction? So here's the spinning disk, omega I. And I should point out, notice they said disk. I didn't have a disk, but I got this wheel with spokes on it. So my shape of my object isn't quite the same as theirs. But the concept of getting it rolling is the same. And so when you place it down on the surface here, what's happening? Yeah, isn't there some, what I'll call kinetic friction? There's sliding going on, right? And what direction is the force on the wheel? Isn't it in that direction? I suppose you would say the table is being pushed that direction. I have a big heavy table, so it didn't actually move in this direction. But if the table was a little bit lighter, I guess when I put it down, it would go something like that, right? And so the table would get pushed that way, and the wheel would get pushed that way. Okay, and so there's my Newton's third law, action and and reaction. Okay? But let's talk about this frictional force. What does this frictional force do to this wheel? And hopefully the obvious thing of chapter 5, doesn't it give it a force which makes it begin to translate? Right? I mean, that's the whole reason it accelerates. And then what else does this force do?
It's heat.
Okay, let's say there's some rubbing and friction going on. Okay, what else? Doesn't it slow the spinning of the wheel down? I mean, if I were just to take this wheel right here and let it spin and put my hand under it, you would say my hand is creating some friction resulting in a torque which is slowing the wheel down. And so this wheel is being slowed down. And that's really what the question is. It says, what is the angular speed of the disk once pure rolling takes place? In other words, it is slowing down. The speed of the spinning wheel starts with omega I, and then as it spins, it not only begins to translate, but it also reduces its rotation. Both are going on at the same time. That's what makes these problems hard, is we got to realize there's not just translation and rotation, it's both at the same time. And so this wheel will rub, 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 and then eventually pure rolling. And so maybe we should pause at that word pure rolling. We used it once before in chapter 10, but what do they mean here by pure rolling? Okay, no kinetic friction, right? There's maybe a static friction here, but there's no more, as you said, heat being generated. There's no more rubbing going on. And so here there is rubbing, 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 and then at some point the speed of the rim is the same as the translational speed, and so it just makes contact, contact, contact. Pure rolling, no sliding that is going on. So keeping that in mind, let's apply the equations to the translational motion. Of course, this brings us all the way back just to Newton's second law, and of course it's chapter 5. If I were to say, what is the acceleration of this? I guess it would just be Newton's law, net force divided by its mass. And in this case, the force in the x direction is that frictional force. And if I were to look at the speed of this object, I would say speed is equal to initial speed plus acceleration multiplied by time. And in terms of translation, I would say that this object starts with no horizontal speed and then has an acceleration of what we just mentioned, the force of friction divided by its mass multiplied by t. And as you guys pointed me out, the time then would be the time needed before pure rolling took place. And so what's happening is this begins to spin, and it rubs, 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 and then pure rolling. Now, granted, there is a relative speed between the table and the wheel that changes, but one thing we learned real nice in chapter 5 is, isn't the friction the same numerical value, the kinetic friction, the same numerical value as long as there is sliding going on? It doesn't matter if it is a lot of sliding or a little bit of sliding. So because of that, I'm going to get the same amount of acceleration, and because of that, I have a constant acceleration, and because of that, I can use this equation. And so I am going to use this equation. This is the friction I get. It's a constant value, and so the t would represent the time, really, until pure rolling takes place. Okay, let's look at rotational motion. Here, I would say I have an angular acceleration. The angular acceleration would be the torque divided by the rotational inertia. Oh, by the way, maybe I should backtrack a little bit. Did you notice I didn't say conservation of linear momentum or angular momentum? Right? Because the friction is down here. When I take this wheel, isn't that friction an outside influence on this wheel? And if I calculate everything from its center, then that is an outside torque. And so angular momentum is not conserved. So keeping that in mind and calculating from this point right there, wouldn't the torque, or at least the magnitude of the torque, be the force of friction times the radius? And so there would be my torque. And since they said it was a solid disk, couldn't I write this as 1/2 mr squared? That's the inertia of the disk. And we derived that one in class. Again, when it comes to the test on Monday, you'll have that little table. And so you have a problem like this, just you can flip to that table and look up for a disk about its center. And so there would be the angular acceleration. I suppose I could even simplify this a little bit. An R would cancel with an R, and the 2 can move upstairs. So that would be the equation for the angular acceleration. Now notice I put absolute value because I should probably ask, how do you want to use our sign convention here? Because if you remember on the translation here, I went ahead and did the standard conventional to the right is positive. So I said it had a positive acceleration. It has a positive speed. However, the rotation I have given it is clockwise. And the convention is to call that negative. But will it be okay if I call that positive? Anybody care? I just don't want to mess up my signs.
And then you call it translational negative, like the direction moves negative, or?
Well, I guess what I'm saying is I just want to make sure these two compare. Maybe I should keep going here. This is the magnitude of the angular acceleration. Fair enough? And if I write the same equation down here that applied to here, I would say for the rotational speed, this does have an initial speed. And then it has this acceleration. But here's the part I need to be careful. How does the direction of the acceleration compare to the direction of the rotation? Yeah, they are opposite. So there's where I got to be careful in making a choice here. Do I want to call the initial speed a negative or a positive? I guess it's kind of my choice here. Why don't I go ahead and call the initial speed a positive number? And so then the acceleration becomes a negative number, and this is its magnitude. That's what I was thinking I would do. And so there, as I said, is my two piece, or my second piece for the acceleration. Now, the final step is to put these together, because This, and maybe I should put a little f here, this is the final speed. That is the final speed once pure rolling takes place. This, maybe I'll put a little f there, because that is the final angular speed. The final and crucial step in all this brings us back to chapter 10, that once pure rolling takes place, isn't the speed of the rim and the speed of the surface the same? See, if the wheel was spinning faster than it is translation, they would be sliding, right? Or if it is moving, translating faster than it is rotating, there would be sliding. When do you get pure rolling? Well, when no sliding is going on. And you get no sliding when the speed of the rim is the same as the speed of this base, or I should say this surface, as seen from the center. So that when the translational speed is the same as the translational speed of the rim, there would be no sliding going on. We did that once or twice in chapter 10, so if I apply that here, I would say when the final speed is equal to the rotational final speed times the radius of the object, that's when pure rolling takes place. So I could replace in this equation omega F times R equals force of friction times time divided by M. Uh-oh, and I just noticed, why did I use a capital M over there and a little m here? It's not like there's two objects here. Oh, I know. Well, I guess because of Newton's second law, we traditionally used a lowercase m. And when it came to inertia, we traditionally used a capital M. But let me backstep a little bit here and point out that there's not two m's in this problem. They come from different ideas where we've been using lowercase and uppercase. But again, maybe that's another good example of let's make sure we're reading the problem, not just doing the problem. These are not different m's here. But here's what's really nice. Watch this. If I take this r and put it on that side of the equation, 1, 2, 3, 4 show up right here. 1, 2, 3, 4. So the final speed would equal to the initial speed minus 2 times the final speed. Move that over to here, and 3 times the final angular speed is equal to the initial angular speed, or put another way, the final angular speed is 1/3 the initial. Yay! There it is. That's what all that led to. How easy is that? Can't wait till next Monday. All right. So again, a lot of deductive reasoning here. Maybe this is a good time to, point it out again. You don't want to memorize a bunch of equations. It's the idea behind them, the fundamental principles, in this case, Newton's second law of motion. Okay? And so if you watch it, you'll see that it's spinning actually pretty fast. And by the time it's pure rolling, it's going 1/3 of that. And so it has slowed down. And that's what this one has to offer. And once you've done that much work, the rest of these kind of fall into place. Part B says, find the fractional loss of kinetic energy from the moment the disk is released until pure rolling takes place. Well, I suspect that's going to be a lot of algebra. So I'm going to come over here and write my conclusion that the final speed is 1/3 the initial speed. And then clear the board. I would love to see these back on here. Let me put a couple of things over here. How about final speed is force of friction times time over m. That's a good one. And then down there, final angular speed. Well, I guess we have that one. How about the magnitude of the acceleration? That would be a 2 times the force of kinetic friction over mr. Yeah, why don't I put those on the side? I think I'm going to need a lot of room for algebra, but I think I'm going to need those pieces of information as I answer the next set of questions. The second part of this one, of 48, is B here. And so they say, what, again, fractional loss? We're back to the same kind of questions they were asking before. What fractional loss? So that would be, if I were to say the initial kinetic energy is equal to the final plus any heat that's created. The heat divided by the initial is what they're asking for. That's the fractional. That would be 1 minus the final kinetic over the initial. So it's 1 minus. Now the initial kinetic energy is probably the easier one. It's 1/2 I omega I squared, right? That is how much kinetic energy does this wheel start with. But after it has rubbed for a while, some of that has turned into heat. And so what is the kinetic energy after the rubbing? Please remember, it is both translating and rotating. And so the final kinetic energy is made up of 2 pieces here. And a good thing about all of this is the 1/2s are the same. And so I've got a 1 minus. And in place of I, I'm going to put a 1/2 mr squared, and then I will go initial speed squared. Up here, I will put an m. But in terms of final speed, if you will allow, let me put r squared times the final speed squared. And then over here, plus I, well, let me do 1/2 mr squared, and then final speed squared. And the purpose of all of that was that there would be an mr squared in every term that can cancel off. And so it looks like on the top I have a final speed squared plus 1/2 final speed squared. Well, that would be 1.5 final speed squared. Downstairs I have 1/2 initial speed squared. That 1/2 would cancel off. So it looks like I have 1 minus, and it looks like I have 3 times the final speed squared over the initial speed squared. 1 minus. Now, the ratio of final speed to initial speed is 1/3. So I have a 1/3 squared. So this must be a 1/9. And so that's 1 minus a third, which is then 2/3. Yay! So there's the final heat energy created in all of that. And actually a continuation of this in the short time we have left is 59. 59 then says, suppose that a solid disk of radius r is given an initial angular speed v0 about a fixed axis through a center and then lowered to a horizontal surface and released as shown in figure 58. So it's the same problem in 59 that we just did in 58. And then furthermore, assume that the coefficient of kinetic friction between the surface and the disk is mu. A, show that the time interval before pure rolling can take place is given by this equation. So the time interval. So coming back over to here, they are asking me to solve for time. And I think this equation will do it. If I write here number 59a, then the mass times the final speed divided by the coefficient, the force of friction, I get the time. And so I'm just going to, in the short time we got left, just write real quickly, this is the time factor. We do know that the final speed multiplied by the radius would be the final translational speed. And we also know that the force of friction is the coefficient times the normal. And since we just set this on a level ground, the normal is the weight of the object. So this would be coefficient times mg. And so that should be the time. And then the m's should cancel off. And then we also know that the final speed is 1/3 of the initial speed, which would then be final speed times r over 3 mu g. Is that what they have here? R times the final speed over 3 mu g. Perfect. And so there's the time it takes for pure rolling to take place. And then finally, show that the distance that the disk travels before pure rolling occurs is this one. We don't really have anything here for distance, but we do have final speed. And so if you remember that final speed squared is equal to initial speed squared plus 2 times acceleration over distance traveled. And if you take beginning speed is equal to 0, then distance traveled is final speed squared over 2 accelerations. And final speed squared is r squared times final angular speed squared. And acceleration, which we don't quite have up there, would be force of friction divided by its mass. Keep working on this in the short time I have. I will go r squared. Final speed squared then would be 1/9 of initial speed squared. And then force of friction would be coefficient of friction times the normal divided by mg. The m's cancel off, and that 9 goes with the 2 to make an 18, and so we get an r squared times a final or initial speed squared 18 mu g, and I think we got the last part of it. Yeah, what is the distance it travels before pure rolling takes place? So good problem that I probably didn't save enough time to. Oh, we got 15 seconds. And so we'll let you go 15 seconds early. Don't let the word get out that you get out early, because then everyone will think this is an easy class and everybody will sign up next fall and we won't have